Okay, since everyone's here, we might as well get started. So, how'd quiz one go? Pretty decent? Okay, cool. Uh, uh, if I don't say remind me, I have your quiz too, and you can take that at the end of the lecture. Any questions since last time? Okay, so the place where we left off last time was we were formalizing the notion of a DFA. What does a DFA stand for?
A definite finite automata?
The first word is not quite deterministic, but yeah, that's right. So we have these DFA things, and we formalized what they were. We had those 5 pieces: Q, which is states; sigma, which is the input alphabet; delta is the transition function; Q0 is the start state; and F is the set of final states. Then we talked about computation. So can anyone give me a high-level version of what a computation is? Yeah.
It's a set of states that.
Yeah, it is a set of states that you visit. Yep. So then we talked about an accepting computation right at the very end, which is you land in a final state. So wherever you end up and you're in a final state, that is an accepting computation. And then at the very end of last time, we talked about the language of a DFAM, which is the set of all strings that that machine accepts. So it's the set of all strings in sigma star such that M has an accepting computation on that string. So here are some test level questions. You probably won't get them because I'm asking you now. Suppose that we have a machine M and a string W. How many computations are there on that string? Just run-of-the-mill computations. The length of the string, well, that tells you how many states that you see. But could there be, if I ran the same machine on the same string, could I have 2 different results of what states I see? No. So how many computations are there?
Wasn't it n plus 1?
That's the number of states. How many different computations are there? How many sequences of states? 1. Because it's deterministic. If you run the same DFA on the same string, I don't know what's going on with that display, sorry. You will go through the same set of states every single time. So you will always have exactly 1 computation. How many accepting computations are there? Let's try that. I'm not sure what's going on with that. Okay. How many accepting computations are there? Well, can there be more than 1? No, because the number of computations is 1. Can there be exactly 1? Yeah, it could be, because the machine can accept the string. What if it doesn't accept the string? It's 0. So the number of accepting computations is either 0 or 1. But the number of computations itself is 1. So what I would recommend for those types of questions is to revisit what the definition says. So when we talked about computations, we said the sequence of states that are visited. So there's only 1 possibility. But accepting, it may or may not be accepting. Okay, so what we are denoting L of M right here. So L stands for language. The language of the machine M is the set of strings it accepts. Okay, yeah, so that's just a language because it's a set of strings. Okay, and probably one of the more important definitions next, a language L is regular. That's the important term, regular, if it is the language of some DFA. So if I tell you that a language is regular, there is some DFA with that language. There could be more than one, but there is at least one. Okay? So it's amazing how many students don't get this. So this is a real question. If I tell you that a language is regular, what do you know?
Some DFA.
There's a DFA with that language. It doesn't mean anything else now. It will mean something else later on, but for right now, it means there's a DFA that has that language, okay? And in fact, your second quiz, you'll be given several languages and you have to show that they're regular. So if I ask you to show that a language is regular, what do you have to do?
Make a DFA.
Make a DFA for it. Okay, yeah.
Never mind.
Okay. So yeah, so a language is regular if it's the language of some DFA. Cool. Any questions so far before we get on to new stuff? So what is a language? Just any language. Like, well, what is it structurally? What's inside a language?
String.
It's a bunch of strings in what structure? It's a three-letter word that begins with is and ends with it. Okay, that didn't work very well. Set. It's a set of strings. Okay? So, in 290, what did you do with sets? Everything. Like what are some examples of things you did? The simplest operations with sets, what do you do?
Power set.
Power set? Like if I wanted to work with two sets? Union and intersection, yeah. So those types of operations. So you may want to think, well, could we do the same types of things with DFAs? If I have two DFAs and I want to make a DFA that is the language of the unions of the originals, so then maybe you can think about, well, if I have a language like this, so if I have a language, say, it's all the strings in sigma star such that W begins with a 1. Let's say the alphabet is 0 and 1. W begins with a 1 or contains 0, 0. Well, what does that or tell us? What is it indicating?
Union.
Yeah, it tells us union. If I can make a DFA for the first part, and I can make a DFA for the second part, and I know how to do union in some sense, then we can solve this problem. We can make a DFA for this problem. Okay, so let's talk about operations on languages. So, operations on languages. Okay, cool. So, we say that the terminology you have to determine it on the fly. We say that a collection of languages C, so C is just a bunch of languages, is closed under an operation, and I'm just going to give O plus as just some random operation, like could be union, could be intersection, could be whatever. we say that the collection of languages C is closed under this operation if applying that operation to languages in C results in another language in C. It's kind of an awkward definition and it's kind of long, but the basic idea here is if you have a bunch of languages you're working with, like regular languages or whatever, and you apply an operation to them, we say that it's closed under that operation if no matter which languages you pick and you work with that operation like union, then you will always get a language still inside the collection. You will never escape the collection. So, for example, so here's an example. So let's let C be the set of finite languages. So every language that has a finite number of strings, not an infinite number of strings. So if I look at the operation, let's just say union, can it be possible that I take two finite languages, union them together, and I get something that's not finite anymore? No, of course not, because at worst, you will just get a language which is the number of elements in both of them added together. So we will say then that finite languages are closed under union. What about intersection for finite languages? If I take two finite languages, intersect them, do I get a finite language? Yeah, of course. So finite languages are closed under intersection, and then we can name other operations and we can figure out whether it's closed under that. Okay, so any questions on what this means? Are infinite languages closed under intersection? Ooh, that's a little more difficult, right? Take the set of natural numbers and have one set be the even ones, the other one be the set of odd numbers. What is their intersection? Empty. Is the empty set finite? You bet it is, but each set was infinite. So infinite languages are not closed under intersection. Okay? So it's just an example of when it's closed under union for finite and infinite, actually, and infinite is not closed under intersection. That's just all I wanted to say. Okay, cool. So we're going to be talking about three special operations called the regular operations. And it's probably the worst title in this entire class of any name given to something. So when you see regular here, it actually doesn't mean the same as regular for DFA. It's just the name given to an operation. For historical reasons, it's called regular. It just happens to be the same thing. And believe it or not, we'll see two other uses of the word regular. But just ignore the fact that it says regular here. It doesn't have anything to do with DFAs or regular languages. So there are three operations here. So the first one is union, which is pretty easy to understand. So if you happen to not remember what that is, L1 union L2 is just the set. Actually, I don't need to say that because it's literally just the union of the set, so you don't have to do anything special with them. So you take all of the strings in one language, put it in, then take all of the strings in the other language, add them into the set if they're not there. So you're just doing normal union. Now let's talk about the ones that are more complicated. The second one is concatenation. Because languages are sets of strings, if you have two strings, well, one thing that you may want to do is put them together, concatenate them. So for concatenation, if we have two languages, L1 and L2, we'll write L1 circle L2 to be the concatenation of the languages. And what does that and what does the language itself mean? It's W concatenated with X, where W is in the first language and X is in the second language. So the concatenation, all it means is we're pulling a string out of the first language, pulling a string out of the second language, and then gluing them together. So let's do an example. So let's just look at L1 being 0, 1, and L2 being 1, 0, 1, 1. And actually, sometimes I'll just drop the circle. So then I would just say L1, L2 right there. But it's common for some textbooks to put a circle there so that you know there is an operation taking place. So in this concatenation language, what is an example string that's in there? Yeah.
0, 1, 0.
Yeah, 0, 1, 0. You pick a string out of the first one and a string out of the second one, you put them together. What are some other possibilities? 1, 1, 0. Yep, that's one. What's another one?
1, 1, 1.
Yeah, 3 ones. And the last one, I think, is 0, 1, 1. And we know that that's true because there are 2 strings in the first, 2 strings in the second. So 4 total, and none of them repeat. So there's no possibility of duplication there. So we have 4 strings, which is what we expect. Any questions on what concatenation is? Okay, because this one is the most complicated of all, and it may take getting used to because it warps your brain a little bit. So the third one is called Kleeney star. I always think Kleenex when I write his name, but Kleeney star. So this is not an operation on 2 languages, it's an operation on 1 language. So what is this? So L1 star, so I'm going to write it informally first, but then I'm going to write it formally. So this is the set of all strings. Taken from 0 or more concatenations of strings in L1. And it's actually exactly the same thing as when we saw sigma star before. It's exactly the same operation, but we're applying it not to just an alphabet, but to an arbitrary language. So what in the world does this mean? This means pick a number at least 0. So let's just say 0. Then you just take 0 strings from the language and then put all the possibilities in the resulting language. Then you pick 1. You pick every possibility of choosing 1 string in the language, put it in. Then every possibility of choosing 2 strings from the language, and then concatenate them together, put it in the language. So let's do an example. So let's look at L1 equals 0 and 1, 0 to keep it simple. So what is an example string in the star of L1? So what string is always in the start of any language? Empty string, yep. So empty string is in there. That was not a good empty string. That's a good empty string. Now, what are the possible ways to choose exactly one string from the language?
0.
0 or, I'm getting a call. 0 and 1, 0, those are the ways to pick one thing from the language. Well, what are the possible ways I can choose two things? And they could repeat. So yeah, go ahead.
0, 0, 0, 1, 0.
0, 1, 0, yep.
1, 0, 0.
1, 0, 0, and?
And then 1, 0, 1, 0.
Yep, 1, 0, 1, 0. And then we could look at the ways we can pick 3 things from the language and put them all together, then the ways we can pick 4 things, and then 5 things, and then 6 things, etc. for every number at least 0. So what can you tell me about the size of L1 star in this case? Does it go on forever? Yeah, because we can just put more zeros on the end of it, of each of the strings. So we can just keep getting longer and longer. Yep. So here's a test question. Or I mean, you may or may not get it, but we'll see. Is L star always an infinite language? So I'm not going to answer that here. I want you to actually think about it, and then we can maybe discuss on Slack. But it's actually a very interesting answer. Okay, so let's define this formally. So what I'm going to define, I'm going to say L to the 0 is I'm going to define that to be just the empty string, the set containing the empty string and nothing else. And then I'm going to define L to the I to be, yeah, how am I going to do this? Okay, yeah. Okay. So it's going to be the union over all, yeah. So actually, no, sorry. I'm mixing up 2 definitions. L to the I is going to be L concatenated with L to the I minus 1 for I at least 1. Okay, yeah, that's what we want. And then L star is just the union over all I at least 0 of L to the I. So that's what I mean to say L star in a formal way. So L to the 0 is just the empty string. L to the I is just concatenating another L onto the previous L to the I minus 1. And L star is just the union over all L to the I. Any questions on any of that? Okay. There's another operation I want to talk about, but it's not a regular operation. Regular operations is just these 3, union, concatenation, and star. For whatever reason, there's no intersection in there, but there's another set of 2 operations I do want to talk about, which is intersection and complement. So I'm going to put in red here that these 2 are not regular operations. The first 3 are, and these 2 aren't. Okay, so intersection speaks for itself. We know what intersection is. What is complement? So here we have a language L, and the complement language, L bar with a little bar on top of it, kind of like a hat, is sigma star take away L. So another way to phrase this is every string not an L. So when I say L bar, that means every string that's not in the existing language. So you have your language L, and L bar is everything else. That's all it means. Okay, any questions on these 5 operations? I know it's a lot. Yeah.
What does it mean to be a regular and not regular operation?
So it doesn't actually mean anything. It's just a name given to those operations for historical reasons. The regular operations, the word regular, has nothing to do with DFAs or regular languages. It just happens to be exactly the same term, which is unfortunate. But yeah, and in fact, we will at some point be applying regular operations to languages that are not regular. So it has nothing to do with it. Yeah, it's just historical. Any questions, though? But we're actually ready now to prove our first result, which is actually pretty easy to do. So our first theorem, yay, first theorem. So regular languages are closed under complement. Well, it must be true because Ryan at the front said that it is true, right? Because I wrote that there, are you convinced that it's true? If you are, you shouldn't be. So just because your professor at the front is telling you that something is true, that does not mean that it is true. Okay? So what would you like to see in order to show that this is actually true? A proof, some kind of proof or explanation or something. So let's see. Let's do a proof then. Well, let's see. What does it mean for the set of regular languages to be closed under complement? What does that even mean? Well, in order to... Go ahead.
I was going to say that regular languages must be in a DFA, and thus, if it's closed, they must remain in the DFA with the complement operation.
Even ignoring DFAs. Well, what this means is, so here's what we want to show. If L is regular, then L bar is also regular. That's what it means to be closed under complement. If we take any regular language and apply the complement operation to it, we also get a regular language. Now, what does regular language mean? Our famous TLA, 3-letter acronym. Yeah.
If it's regular, then you can make a DFA.
There's a DFA for it. So this is what we want to show. But this is equivalent to saying a DFA for L, then there must be a DFA for L prime. I mean L bar. Cool. So, do we know anything about the DFA for L? other than the fact that it exists? Do we know how many states it has? Do we know its alphabet? Do we know transition function? Anything? No, but we can give a name to each of them, each of those 5 parts. So let's see. Since there is a DFA for L, call it M, and I'm going to give a name to each of the parts. Q, sigma, delta, Q0, F. I'm just giving a name to each of the parts, whatever they may be. I don't know how many states it has. I don't know what the start state is, what the final states are. I don't know anything. Well, let's see. How can we produce a DFA for the complement language? Let me revisit a question I asked you not too long ago. How many computations are there for a DFA and an input? Exactly 1. Well, let's see. Well, what could possibly happen in this DFA on some string? Well, here's what could happen. Well, we have to start in the start state, right? Then at some point, we reach a state, and then we're done the computation, right? We do some number of transitions, and we stop at some state. Well, what could that last state be?
0. I mean,
Yeah.
accepted or whatever, not accepted.
Right. It could be either accepted or it isn't an accepting state. So here's case 1, and the other case is case 2, where we end up in a final state. Well, let's see. Well, for the complement language, I want every string that ended up in a non-final state to now end up in a final state, and every string that went to a final state before, I now want to have it go to a non-final state. So what do you think we can do? I don't know anything about the structure of the DFA, but what could I do instead?
Swap all the final states.
Yeah,
All the states just be like
right. Well, let's see if that works. That seems like a reasonable idea. Take every state and then flip whether or not it's a final state or not. If it was 1 before, it's not 1 now. And if it wasn't 1 before, now it is. So here's how we can notate this. Let's create a DFA M bar to be, well, I don't want to change anything else other than the final states. So the set of states is the same. The alphabet's the same because I'm not changing that. I'm not changing any of the transitions. The start state is exactly the same state, but whether or not it's a final state will change. So the set of final states now is everything that wasn't in F before. How do we write that?
It'd just be F bar.
F bar, but another way I can write that. Well, what am I complementing with? The set of states. So it'd be the set of states take away the final states. You have to know what ground set you're working with.
So it would be Q take away F.
Exactly. Yep. So it'd be Q take away F. So the set of final states in this guy is every other state. And the original final states are not final anymore. Does this work? Again, how many computations does a DFA have on a string? And I'm holding it up. 1. So can it be possible that the M DFA, the first DFA, fed on a string goes to two different possible states it ends up in? No, it only has one possibility. So whatever that possibility is, it now does the exact opposite thing in M bar because there's exactly one computation. If there were two computations, can I claim that? No, because there's only one computation. Now I can guarantee that. So because exactly one computation for each string, the language of M bar must be L bar. And that's it. It turns out that idea worked. Thank you for that. Any questions about how that worked? We can do a short example. You want to do a short example? Okay. So let's do an easy one. So how about this language? So all the binary strings, so 0, 1 star, so here's an example, where W contains 0, 0. Okay, well, first off, we gotta make the DFA first for the language. So we need a start state, so we need Q0 here. Anyone have an idea of how to make a DFA for this? Yeah.
It's just like you have a Q1 and like actually.
Yeah, go ahead.
You would have a Q1 and a Q2
Mhm.
of where if it's a 0, it'll go into if Q0 has a 0, it'll go to Q1,
Mm-hmm.
and if Q1 has a 0, it'll go to Q2, and Q2 infinite it on itself.
Right. So here's a pro tip. I'm not a pro, but it's a pro tip. Whenever you have the language W contains something, or something like that, then make the path of transitions that leads to acceptance first, and then fill in all the other ones next. So in this case, what you do is you make the path of 0, 0, which leads to an accept state, and then fill in all the other transitions after that. So focus on the things that will lead to acceptance first, and then focus on things after that, all the other transitions after. So as was pointed out, Q2 should be an accept state. And once you see 0, 0, then that means that we've seen 0, 0, and so therefore anything that appears after that, I shouldn't ever leave an accept state. So I'm just going to loop 0, 1 on that. And what about the other two states for one transitions?
One for Q0, one would go back to itself.
Mm-hmm. Yep.
And then for Q1, if it's 1, then Q1 will
Go back to Q0. Exactly. Good. Cool. So what could we do with this? Well, if we want to build the complement language, which is all W's such that W does not contain 0, 0. Make that C better. And now you think, oh boy, now I have to think about all the cases of what could happen here. Or is there an easier way?
Just flip all the states.
Yeah, it's super easy now because we have that technology. of the theorem we proved. Don't you love notability? You can just paste pictures like this. So now I'm going to invert all of the states to be final and non-final. So Q2 is no longer final. Q1 is final this time, and Q0 is final now. And we can do a mental check. If you have 0, 0, then you're going to take the Q0, Q1, and Q2 transitions. And so, which will go to Q2, but Q2 will never leave that state, and therefore there's no way to accept. Another name for a state like Q2, where it's not final and it just loops on everything, this is sometimes called a dead state. And people think that this is actually a little too, not the best word, so to speak. And I actually tried to get this into a paper of mine, but I wasn't able to. Another term you'll see in the literature is cemetery state. But unfortunately, the paper now has dead state in it, but I tried to get cemetery in. But okay, any questions on this? So it's a pretty simple procedure. You just flip whatever states you have to be final and non-final. Don't even touch the transitions. Pretty cool. Okay, so let's tackle union. And I'm not sure how much we can get through that. We will continue it on Wednesday, but I want to at least see how far we can get today. So union, what does that mean? That says that L1 and L2 being regular, if we showed that it's closed under union, then that means that L1 union L2 is also regular. Now, I'm not claiming that this is true, but if we were to show that regular languages are closed under union, that's what this would mean. So here's an idea that does not work. I'm telling you in advance it does not work, but I want you to tell me why. I want to show that L1 union L2 is regular. But because L1 and L2 are regular, there's a DFA for both of them. So here's what you do. You feed the string, the input string, into the first machine for L1. If it says yes, we accept, then great, it's in the union. If it does not say yes, now feed the same string into the machine for L2. If it says yes, then great, it's also in the union. If both machines at this point have said no, then it's not in the union. What's wrong with that idea? Well, at least one of the two machines is saying yes, and so therefore it is the union for sure. But there's something else going on. How did the second machine start?
It only started because the first one failed.
Because the first one failed. Well, what happened? The first machine read through the entire input. Can the second machine resurrect the input? Or is it that once you look at a character and take that transition, it is gone? Yeah, once you read a character, you can no longer resurrect it. It's gone. So if there is some way to get this to work, then it has to work by reading the input in one stroke. It can't like resurrect the input and try again. If it could, then this method would work. But, oh, well, so therefore, since that one method didn't work, it's not closed under union. Is that right logic? No. You see this on the news all the time. This one method didn't work, and I can't possibly think of another method, therefore it cannot possibly work. Is that right logic? No. So we're going to have to use our big brains for this. Big brain moment. So what could we do? Well, let's do an example. A really small example. How much time do we have? Okay. And I'm arranging these two DFAs for a reason. So I'm arranging one horizontal and one vertical for a reason we'll see. Well, let's see. Suppose we have the string 100. So our input string W is 100. Well, what is the first machine? Where do we end up in the Q machine, the Q0, Q1 machine? Where do we end up after seeing 100? In Q1, good. And we figured that out because we start in Q0, 1 takes us over here, 0, 0. What about the second machine? Where do we go? Yeah, well, let's see. So we're in R0 to start with. We read a 1, so we stay in R0. 0 takes us down to R1. 0 takes us back up to R0. So we end up in R0. So is this string in the union? Yeah, because the Q machine says yes, and so therefore it doesn't matter what the R machine says. What if we looked at the string instead 1, 0? Well, what does the first machine say?
No.
It says no, we end up in Q0. What about the second machine? It says yes. So is it in the union too? If only there were a way to test both of them at the same time. Ooh, wait, that's an idea. Can we test both machines at the same time? So an analogy for this is I put the Q machine in the right half of my brain and the R machine in the left half of my brain, and I'm simulating both machines at the same time. So here's what you will do. Well, let's make a state for looking at pairs of states in the original machines. So we're going to, in principle, simulate both machines at the same time. Well, here's what we can do. Well, at the beginning, if I simulated both machines at the same time, what state am I in both machines to start with?
False. Or I guess
No, what is the names of the states I mean?
Q0.
Q0 and R0. So if we're going to simulate both machines at the same time, so I'm right now in Q0 and R0 at the same time. Well, let's look at the 100 string. Well, if I take a 1 in both machines at the same time, well, what does the Q machine do? It goes to Q1, good. So Q1 is my state in the first machine. Well, what about the second machine? Goes to R0. Oh, wait. So then we're just keeping track of which state we are in each of the machines. Could I, for example, make this a state and this guy a state and put a 1 in between? Could a 1 from those two initial states ever do anything different? No, because the original two machines are DFAs. So there's only one possibility for each of them to go to. Q0 only has one thing it can do. R0 has only one thing it can do. So that's the idea we'll visit next time, called the product construction. So I'll see you on Wednesday.